So, we are discussing analytic tabula and then we have proved some set to be inconsistent, but the definition of inconsistency and consistency should be looked at exactly the way we have defined, that should be taken that way only. Like you say that a set of propositions is inconsistent. So, now it is tabula inconsistency, not PC inconsistency. So, it is told to be inconsistent if there is a closed tabula for the set of propositions. Okay. So, all that you want is you construct one such tabula which is closing, that is what you want to check. And for consistency, just its negation, that you have to see whatever tabula you construct, it remains open. Okay. Every tabula for the set of propositions remains open, it is never closed, then you can say it is consistent. So, okay, for inconsistency it will be then easier, right. For example, let us see one more. So, this set is inconsistent. So, we will be constructing a tabula for this. We just start with all of them at the root. Okay. Then go on applying the tabular rules. So, now I see not R, not T, they are already literals, and there are 3 others which are compound propositions on which tabular rules can be applied, and all of them are branching. Okay. So, any one of them I can choose and proceed. So, let me choose this one, it is smaller. So, this gives 2 branches, one is not S, another is not B. Is that okay? Because all that you remember is if it is in the form A implies B, it is equivalent to not A or B because of the semantic trees. So, then it will have 2 branches, one will be not A, another will be B. Okay. If you forget the tabular rules, then you can reconstruct it that way. Now, what happens? Nothing is closing really. Okay. We have only T, not R, then not S, another path is T, not R, not P. There are of course other propositions in the path. Then one more we can start with. So, I will start with this one. Okay. They will be same of course. Let us try. So, this one gives again 2 branches, not of not S and T, another is Q. Okay. But now, if you go to the other path, you wanted to expand it breadth first, then once you are using it, that again you have to add here. Okay. So, let us do that. Fine. So, again this one gives 2 branches, not S and not T. Okay. Same way this. Fine. Is that right? So, now this path closes because not S and not S. So, that closes. This path also closes because it is T, not T. Same way this. We have now 2 other open branches, open paths. I have Q, not S, not R, T and this. So, there I have used S implies not B, this also has been used, first proposition has not been used till now. Fine. So, we can still expand this path, right. So, let us expand that path. I will take that path here. So, on that I have P implies Q implies R. So, that will give rise to 2 branches, not of P implies Q and R. This one, it does not close, no, there is no not S, not S is this side, this is not closing, only this is closing, not T. Yes, good. So, that also you have to expand again. Okay, let us see this. First one is Q, which is open. There we have this, that gives rise to again not of P implies Q, not implies role, that will give 2, one is P, another is not Q. So, one is P, another is not Q. Now, this not Q is closing, right, there is Q there. Anything else is closing? It is here, this path we are taking there. Okay. So, we have T, not R, not S, Q there, not Q has closed. Okay. What about P? That path still remains open. P and not Q, right? It is not opening branch, they will be on the same branch, right? So, both the things will be there. You can write P this way and not Q this way, or sometimes we do not write this vertical bar, we just leave it. Okay. Now, you see that closes with Q itself. So, there is no open path there. What about the other side? There is R. You have not R on the same path, right? So, that also closes. Now, what about this Q?
Same, not R is there.
The whole thing will be copied there, because there we want to apply this also. So, the whole thing will be coming here. That subtree what you see here, that is also for the other Q. Fine. You have to take another copy really. On same page of paper, you have to do it exactly. Fine. So, that means this set is inconsistent. Okay. Huh? Not S is there. So, you have another branch. There again you have to expand. So, now suppose you expand it. What happens there? Again you have to come to this place. Okay. So, again the same copy will be there. Now, once it is there, what do you get? It will close with
One will close with R.
P will close with not P, right. What about the other one, that is R and that is not R. Is it clear? The same copy will be here again. Okay. Now, there you have P not Q and R, P not Q in the same path. So, P not Q, with that you have not S, you have not P, that closes, and with the other one you have R and you have not R here, that also closes. Okay. Is that clear? So, now for consistency what should we do? Let us start. Say I take only this much. What should I do? So, we start the tabular now, but the tabular copy is there already. Can you see there? Suppose I do not have this, I have only 1, 2, 3, 4 propositions. So, for those 4 propositions I have already made the tabula here. Okay. The first proposition was never used till now, therefore, this is the tabula. Okay. In this tabula what happens? I have a closed path, closed path, closed path. Now, there are 3 other open paths. Fine. Now, from this can you say that it is consistent or not? Yes. See, I can tell now, because all the compound propositions have been expanded with, they have been used, right. Suppose it is not that, I have not done up to that, I just stay here, I just prune the tree, I do not expand, I keep up to this place. Now, I say that this tabula is also open, because this is also a tabula for the same propositions, same set of propositions.
But they have not opened up there are still some common.
I have not used them, right. But as a tabula, it says it is an open tabula. Up to this also it is an open tabula, right. But here you are telling, you will decide that it is consistent, but up to this stage if I take, you will say it is not decidable here. you have to go for some more steps, right. The reason is you have not used some of the premises, right. So, that amounts to telling that a tabula should be completed, is it right. If the tabula is completed, then only you can decide whether it is consistent or inconsistent. A completed tabula if remains open, then it has to be consistent, because essentially what happens, for consistency you need that every tabula should remain open, not the completed tabula or any completed tabula, you want every tabula to remain open. Now, if you take a completed tabula, then essentially it has a copy of all the tabulas, okay, because all the premises have been used. So, whatever way they can be expanded, either they will close, or if they do not close, then that open path will be still present in any other tabula, fine. That is the reason we say that it is consistent when some completed tabula remains open, you do not have to go for every now. So, completed tabula becomes helpful, fine. Let us see one more example, how to decide this, say Q or R. So, we start with this set, we do not know whether this is consistent or inconsistent. So, if you guess that it is inconsistent, then you just go for one construction of the tabula. If you are not able to guess, you will be going for the completed tabula, right, where on every path a rule should have been applied on the compound propositions, okay, that has to be seen, then it is a completed tabula. But you do not need that, even if before that it closes, then you stop there, because a completed path is one which is either closed, or if it is open, then all the compound propositions, on all the compound propositions rules have been applied, fine. So, that is what we are going to do. So, let us start the tabula, say I have to take all those propositions at the root, fine. Now, you go for say branch out from this one. So, I get not T U, okay. Let me take the other one after this. So, that gives me not R and S and T here also, fine. Then I can proceed, say S and T, I will break down. I have not yet checked where it is closing or not, is it closing? Yes, not T, with T it is closing. So, I do not have to expand this further, this also I do not have to expand, okay. So, there is one more, this is to be used. So, let me use it now. So, it gets not P and Q or R, again here also not P, Q or R. Now, not P is there, you do not have a P there on the path, and here also you have Q R, here again you have Q R. Is it a complete tabula? Completed tabula? Each path should be completed. So, this path it is closed, so it is completed. This path is open, okay, but on every proposition occurring in that path, every compound proposition tabular rule has been applied. Therefore, that is also completed. If you take any other, say this one, so Q or R is another compound proposition, it need not be the premise, it can be obtained from another premise. So, on that also it has been applied, on all these that is also applied. So, that is also a completed path, but open path, right. So, we decide that yes, it is completed, but it is open, therefore, the set of propositions is consistent. Okay. See, you can also make it very mechanical. The way we have done is, we have just chosen whichever is convenient for us. This I thought will be convenient, it is giving rise to only two literals directly, so I use it and so on. But when you do it by a machine, it is not able to find out some such heuristic, right. Of course, you can give those heuristics, fit the algorithm with some heuristics like that, but let us have a crude algorithm which says you just start the tabula systematically, take some ordering of the propositions, whichever ordering you decide in the beginning itself, do not change it later. Now follow that ordering, go on using the rules. Okay? But there is one thing which we have to modify that. For example, we have taken not P, Q or R. This comes from the premise P implies Q or R. Okay? Now immediately we take Q and R here, those two paths we have taken. So imagine we have not used it at the last, but used it at the beginning, right. I can start a tabula from there itself. Say I take a copy of that here. Okay. Suppose I use the first one. So there I will have two branches, one is not P, another with Q or R. Okay. Now what happens? You can apply a rule here directly instead of going further using other premise, but in a systematic tabula we will not do that. We want to see that all the premises have been used slowly, and then we will develop it pathwise. We look at a path, see whatever is the compound proposition from the top, use a rule on that, right. That is what a systematic tabula is, because what happens here in propositional logic it does not matter, but later suppose you will have some opportunity to reuse the rules, right. The same compound proposition can be overused many times, it will give rise to different conclusions. Okay. Like suppose you say for each x p x in natural numbers, I could have taken p1, I could have taken p2, I could have taken p3, and this is infinite. So if I proceed from px, what to conclude? I say p1, p2, p3, where to stop, right. So we will make it systematic, so that it can be again extended to first order logic later, that is the reason. So what we do here, we will not apply a rule on the recently got premises or whatever has been obtained from the rules. We will start again looking at the path, from the top of the path you go on finding the compound proposition, apply the rules, follow it systematically, right. So let us see how does it look like. There is one more difficulty. Suppose your set of propositions is infinite, then what will you do? There will be problem, right, in applying the rules and thinking that the tabula will finish there, but it is possible that the tabula still will become finite if it is closing, everything is closed. After that there are only redundant propositions. I have P, I have not P, after that everything is redundant, right, it will simply close. Okay. So similar thing can also happen even if the set of premises is infinite. Okay. So let us think a bit how to give the systematic tabula for the infinite sets even directly. So anyway it will be a countable set, because the set of propositions is countable. So whatever set you take, set of propositions, subset of the set of all propositions will be countable. So in that you can have an ordering, right. So let us start with a set of propositions sigma. So let us write sigma equal to x1, x2 and so on. So we are thinking of this as an ordered set now. The way it has been written, that is its ordering, right. X1 is the first one, x2 is the second one, x3 is the third one and so on. Okay. So now what do we do? We will define the generation of systematic tabula in stages, because there are infinite things. So each stage will be defined inductively after one stage, right. So first stage is this. In stage 1, what do you do? See, the problem is we cannot take everything at the root the way we are doing earlier. So you have to start with one, that is why the stages, right. So introduce x1 or take x1 on the root, x1 as the root. Okay, we start with that. Then in stage n, what will it do? In each stage we are introducing one, then we are expanding. starting from the top. Okay. So, in stage n plus 1 we assume that x n has been introduced already or stage n has already been performed, then we are going to do in the next stage, that is what we are concerned with, right. So, suppose stage n has been performed. Fine. Now, in stage n plus 1 we introduce, where to introduce really? Suppose you want to introduce x n plus 1, right. Where will you introduce? All the open branches. If some path is already closed, there is no need to introduce there, right. Is that okay? So, that is what we are going to do. Fine. Then in stage n has been performed, first you have to check after this whether any path closes. If closes, you do not have to do anything, right. So, first check that, check whether any path is open. That is the first thing to do. Then for each open path you have to do something. So, for each open path row, let us call it row, expand the path as follows. So, how do we expand? First we have to introduce x n plus 1, right. So, introduce or just add whatever you write x n plus 1 to the path as a leaf, of course, right. Your introduction will be on the leaf level always, not from the root, that is what we are following. So, introduce at the leaf itself, x n plus 1 becomes the new leaf now, it is a child to the earlier leaf, whatever leaf was there on the row, fine. Then what we do? Scan row from root to leaf, for a compound proposition say A on which a rule has not been applied. Okay. Suppose that is the first. So, you are scanning from the top root to the leaf, top down way, on that path only row, not other paths. Other paths we are forgetting now. We are trying to expand only that path, and each path we will have to expand anyway, right. So, on that path from the root, when you proceed, you find one A compound proposition on which rule has not been applied. Then apply the rule, add the child or children, whatever it is. If it is a stacking rule, then there will be one child or two maybe on the same path also, right. But if it is a branching rule, then there will be two branches out from the leaf. So, add those child or children, whatever it is, add suitable child or children, or you can write propositions. Once you write suitable, that takes care of propositions to the leaf of row. Now, it is really for x n, x n is at the root now, leaf x n plus 1, right. So, leaf of row, this is how you expand. So, one step of the expansion is over. This is what we have to perform in stage n plus 1, right. But there is one condition. Condition is, suppose sigma has only n number of propositions, then you cannot find x n plus 1, right. So, that is the condition. If there is at least x n plus 1, then use it, For infinite only we are thinking. For finite case there is possible that at a stage all the propositions are over. So in x n plus 1 all that you have to do is look for the compound propositions and go on expanding it, right. So if it cannot be further expanded, stop there. Yes.
Anyway, expanding at each stage. So why will you get a later?
You are not expanding totally. Suppose you want to come to here, P implies Q or R. So at one stage it will give you not P, Q or R, Q or R remains. We are not expanding at that stage, only one from the top. So it may be expanded in the next stage or maybe later, I do not know when, right. Again I have to come from the top, I get this one first, right. That is why it is systematic. We are not worried about whether it is finished or not. Okay. So we should add something here. Introduce x n plus 1 to the path as a leaf, provided sigma has more than n propositions. If it does not have, then stop there. Now let us look at this place. So there is when this algorithm will stop, when you cannot further expand it, right. So if no such A is found out, then stop expanding row. Now for each path we are doing that. Okay. So this is only inductively defined, it does not say that at any stage it will stop, it may not stop even, right, because sigma is infinite and it is consistent sets, then it will not stop, it will go on forever. Imagine P0, P1, P2, P3 all propositional variables, right. Now you will introduce at each stage one proposition, continue, no expansion is required, still it goes on infinitely, right, one path only, it is all stacked and it is continuing infinitely, there is an infinite path. Is that clear? So anything is possible there. Now let us see your question, what happens here, how to develop a systematic table for this set. Okay. So suppose you take these propositions as they are ordered, that is my sigma, as they are written, that is my ordering. So I start with the first proposition, which is P implies Q or R, that finishes my stage 1. Okay. So let me write here my stage number just to keep my documentation. In stage 1 I have introduced this. Now what I do in stage 2, I have to introduce second one if there is possibility. Suppose nothing is there, right. So again it will go to stage 2, I have to write stage 2, apply the rule, there is nothing to introduce, fine. If there is something I have to introduce that. So I introduce in stage 2 not R implies S and T, but stage 2 is not over, I have just introduced because there is one. Then what I have to do, for each open path I have to do something. So this is the only path that is open. Now I should go back to root, from root I have to scan which one is the compound proposition on which a rule has not been applied. So I find first proposition, which is my A now, it is a dynamic variable there, so it is my A. There I apply the rule, so I get not P, Q or R, both of them have been obtained in stage 2, they are in stage 2, right, nothing more. It does not say you do it again.
Oh, okay.
It is not a loop, it is telling that it is stage n plus 1, that is all. So suppose that stage has been performed, I have to go back again, follow the procedure, the loop will be on n directly, not there itself, there is no sub loop there, okay. So second stage is over. Now I come to third stage. So in third stage what will happen, there is another, so I have to introduce that. So everywhere, it is not over. I have to again scan on each open path on which a compound proposition, on which a rule has not been applied. So, first one I have already applied in every path. I am doing it breadth first, so that will be easier to look, easier to see it at least. Then second one I have not applied on this path, it is done daily pathwise. So, on this path it has not been done. Now, I apply it, that is again in the third stage. Okay? That is again in the third stage. So, it will have not R, S and T, all these are done in third stage. Here also there is another open path, same proposition is taken there, S and T, they are my third stage. Okay. Third stage is over, that is the only thing I have to do. So, anything is closing, that has to be checked always, nothing is closing till now. So, I go to fourth stage. Fourth stage, there is the fourth proposition. So, I have to introduce fourth stage. So, that gives T implies 0, T implies 0, T implies 0, T implies 0. Fourth stage starts with that. Then what I have to do? This is over. I have to look at each open path. So, one open path is here, the leftmost I am taking, where I have to find this compound proposition, rule has been used, rule has been used, it is literal, literal, this is not a literal, not. Everything might be obvious for us, but not for the algorithm. So, on the fourth stage I have to write R, this is done. Okay. We have not rule, a rule can be applied, so I have to apply it, and I forget about that for that path in that stage. I come to next path where I have to find similarly. So, here again I get S and T. So, that is again fourth stage S T. Okay. So, that is also done. So, different propositions you might get in different paths, that does not matter. So, next open path I take, there Q or R, that is also in fourth stage Q R. Okay. And this path same thing Q or R. So, that is again fourth stage as Q, fourth stage as R. Fine. Next I go to fifth stage. So, there is nothing more to be introduced. Now, I have to first check whether anything is closing out of this. Anything is closing? Nothing? This is closing, T and not T, right, that is closed. Next about this, I have Q not T, nothing is closing, R, nothing is closing, right. Next path again Q R, nothing is closing, they remain open, right. So, next I have to check each path whichever is open. So, usually the leftmost we have to take, algorithm really says you start from the leftmost path and then continue. So, then I have to take this open path, find out on where I have not applied a rule, apply it, that is the fifth stage. So, this is the proposition on which I have to apply a rule, not T U. Okay. That is all about the fifth stage. Closed path I do not worry, open path. So, these two have been applied, not T, not R. So, I have to write R. That is all about the fifth stage. Then here again same thing, fifth stage R. It just does blindly, no intelligence. So, next one is again S and T. So, fifth stage will be S, fifth stage will be T, and here also same thing, S, T. That is about the fifth stage over. Now, we have to again check whether something is closing or not. This one is not closing, U are not closing, that is also not closing, right, R that is also not closing, S T Q not T closing, T not T closing, right. So, fifth stage is over. Sixth stage I have started while we are finding out which paths are open or closed. Now, in the sixth stage I have to go for the leftmost path. I see everything has been used, there is no other compound, right. Next path everything is used, next path there is one not used yet, so use it, that is sixth stage. Here also same thing, sixth stage. Okay, sixth stage over. Now, seventh stage starts. So, this does not close, this does not close, nothing is closing, nothing is expanded, over, it closes. So, that is also another way of telling the stopping criterion. If you get same open paths as the last stage, you can stop, because in the next step only you are verifying the whether some path is closing or not. Now, you can compare this systematic tabula with the one you had already constructed earlier, this one, right. Systematic tabula will be bigger, that is clear, does not matter, but there is a copy of this tabula inside it somewhere, may not be in the same form, same order, something else might be inside, because they have closed early, so they can expand, that is fine, but then a copy is there. So, systematic tabula is necessarily a completed tabula, right, it has to be completed, but that you are guessing only from the finite case. If it is infinite case, how do you justify that a systematic tabula is necessarily a completed tabula, but you take any systematic tabula, it has to be completed. Why is it so? Well, if it is not completed, then what happens? There exists at least one path which is not completed, right. So, it is not a completed path, means what? Okay. So, that compound proposition has been obtained by the tabula either there or it is originally in the sigma. If it is originally in sigma, then it should have been introduced in some stage, right. So, it has been obtained. If it has been obtained, then from the root to that place whatever is the number, say m, then it will be used in stage m, right. So, always we are concerned with the finiteness, even though tabula look infinite, we are really can get away with finiteness, fine. So, now systematic tabula is completed. Once it is completed, what you have to do for consistency? You just go for the systematic tabula and then decide if there exists an open path, then it is consistent. Only thing for infinite, what to do?
You cannot have a systematic tabula at all.
Why not?
You can only check. In the sense you can never you can never complete the systematic tabula.
You can check only if it is inconsistent. Yeah, you cannot check for consistency.
Yeah, if it is a consistency.
Yeah, if
Yeah.
it is consistent, then you can't.
You can't
If it is inconsistent, then it will close, everything will close in a finite stage. So, it is verified, otherwise it may go for infinite. If it goes for infinite, can you say it is inconsistent or it is consistent?
No. There might be a future.
You cannot
There might be a future
Yes.
xi which might be.
You cannot say.
Basically, we don't know whether it will stop or not.
Yeah, you cannot say.
No, it need not stop. It is infinite. You are telling it is infinite. So, there is one infinite path. Let us say in the tabula there is one infinite path in the system, in a systematic tabula. Now, does it mean it has to be open or it is closed, or it can be anything? If it is anything, it will close at some finite stage. Once it is closed, it has to be finite. Why is it so?
Why will it close?
It can close, but it cannot be complete.
Huh?
Are we considering
Just
infinite number
complete
of
story.
are we considering infinite number of literals or a finite number of literals with an infinite number of superpositions?
There can be infinite number of literals also, right? As we told, there can be a set with P0, P1, P2, P3 and so on,
So you cannot see.
right? Suppose you say one path is closing, there is a path which is closed. Is it necessarily finite? It is finite. No? Path is finite, isn't it? Yes, path is finite or not? Huh?
Yeah.
If a path is closed, is it necessarily finite? Yes? Then if there is one infinite path, it has to be open?
You cannot determine whether that path is infinite or finite.
That is a separate matter.
If it is given infinite, then it should be open.
Is that so?
Yes.
Yeah?
Either finite or infinite.
Whether it is finite or infinite is the problem.
That cannot be found.
So you are not able to decide whether it remains infinite or it remains finite. But it is true that if it is closed, it has to be finite.
Fine.
Yeah.
That is
Right? If it is infinite, it has to be open. Right? There can be finite open paths. That is okay. Right? If set of propositions is finite from the beginning, yes. Fine? Okay. So what we see here is from the systematic tabula, we have to be concerned about this finiteness thing. Right? Finiteness closed, finiteness open. Okay? Now there is something which we may need, because finiteness is not easy to look in the tabula itself. Okay. So finiteness will give you something more there. We will see what does it mean. Let us take any general tree, what happens there. See, all these tabula are binary trees, right. So you have a binary tree here. In that binary tree, you are telling whether it goes to infinite or not, I do not know, right. It is an infinite binary tree, and then I do not know what happens, whether one path remains open or not. Okay. Now if it is not a binary tree, you take any general tree and you know that it is finally generated, that every node has only finite number of children. How many you do not know? Can you tell in that case something? I am slightly asking a difficult question, but it might be easier to see. See, you have a binary tree here. That means you take any node, it has less than or equal to 2 children, right? Maybe one only, less than or equal to. Now consider one finitely generated tree, which means you take any node there, it will have finite number of children, not infinite number of children, right, as usual. But that finite number I am not giving what it is. There may not be any bound, right? It can grow, like from level 1 each one will have one child, level 2 each one will have 2 children, level 3 each one can have 3 children, and so on. But this is also finitely generated. Is that clear? Possible?
Random.
It is random. I am giving an example that you cannot say there is a maximum number of children of anyone, right? That is possible. Then in that case, what can you say about paths? Suppose the tree is finite or infinite, I give something, say tree is infinite. Does there exist one infinite path or not? Why is it so?